Hello everyone, we are Team 5 for Lab L02. I am Tarara and my group members are Mitchell and Marshall. We will be delivering a progress report for an independent review of a cooling system. The goal for Burdell Incorporated is for the system to cool an object using mechanical work. The Client Machine Chillers Incorporated has developed a system that works with gas-only working fluid to replace toxic refrigerants. To achieve an independent review, the firm will experimentally characterize the compressor's ability to pressurize the system while determining the motor voltage and pressure relationship. Experimentally characterize the vortex tube input and output properties, such as the relationship between input pressure, output temperature, and mass flow rates. Experimentally characterize the heat energy transfer at the load, such as determining the thermal resistance of insulation and other load material properties. And finally, conducting an uncertainty analysis for all the values used in calculations. On the left, our experimental setup is shown, including the vortex tube, motor, and compressor. The motor and compressor create pressurized air so that air is drawn out through the suction valve at low pressure and discharged through the discharge valve at high pressure. Our analysis of the system is divided into 2 weeks. During week 1, offset values are calculated for each sensor, ambient temperature is measured using a thermometer, and ambient pressure is found with local conditions. The system is run with input voltages ranging from 0 to 2.5 volts until it reaches steady state, and the steady state relationship between input voltage and pressure is determined. We will also be determining the heat transfer rate due to ambient heating through an insulation block, as well as comparing theoretical and experimental thermal resistance values. We will then conduct an uncertainty analysis and derive equations from experimental observation to do this. Here we can see a diagram of the system and connections of the sensors to the Elvis board. The vortex tube separates compressed air into hot and cold uncompressed streams. The pressure input is at station 3 and is kept constant during the test using an accumulator tank. Using a heat exchanger, the temperature at this point is equal to ambient temperature.
Here we can see the offset values calculated before week 1 data was collected. Offset values will be compared between week 1 and week 2 to account for any possible changes in the system over that time. Now we will present the analysis on the steady state behavior of the compressor and the vortex tube. These figures show the steady state relationships between the input pressure P3 and the cold and hot output temperatures. As shown, a linear fit matches the hot temperature data but does not fit the cold temperature data. A quadratic or non-linear fit would be a better representation for the cold temperature data based on these results. Additionally, as expected, the hot output temperature linearly increases as P3 increases, while the cold output temperature decreases as P3 increases. These figures displayed are the steady state relationships between the input pressure P3 and the cold and hot output mass flow rates. A linear fit more closely matches the cold output mass flow rate data than the hot mass flow rate output data. Despite the linear fit being close to matching the hot output flow rate data, a nonlinear fit will be investigated and compared to the results shown. As expected, the cold mass flow rate is linearly increasing as P3 increases, and the hot mass flow rate also increases as P3 increases. This figure shows the steady state relationship between the input voltage and the input pressure P3. This relationship is fairly linear and matches the fit well. However, the input pressure starts to level off or becomes constant as the input voltage increases. This indicates that the compressor could be approaching its limit in terms of pressurizing the tank. Based on the steady state behavior of the vortex tube, we've made the following observations. T3 increases, but not significantly, between 0 and 2.5 volts. This means the heat exchanger is working well, and the vortex tube does more work to separate hot and cold air at higher voltages. Secondly, T1 increases as the input voltage increases, and there is a non-linear trend between the two variables. This shows that the compressor is more effective at lower voltages. Another observation is that there is only a 0.4% decrease between P4 of cold and P5 when the system is at 2.5 volts. This means that we can still validate our thermodynamic assumption that there is a constant pressure across the load. Now we will present analysis on a refrigerated load. Here are our calculated experimental and theoretical insulated resistance values. Experimental insulated resistance values are initially calculated using a thermal conductivity value of 0.033. The theoretical value is calculated using dimensions of the styrofoam. There is no trend between the insulated resistance values and voltage, as insulated resistance is independent of the test pressure. The theoretical insulated resistance values is significantly higher. This is because the physical insulation is not working as well as it's modeled because the top is exposed. Here we have values of heat transfer rate due to ambient heating for each input voltage. There is no noticeable trend between Q ambient values and increasing voltage. This is because of reasons explained on the previous slide. On this slide, we can see our calculated experimental thermal conductivity values using the experimental insulated resistance values for each input voltage. Thermal conductivity values are not consistent between tests, but they generally decrease as voltage input increases. Finally, we have our values for the heat transfer rate due to ambient heating, which is calculated using the theoretical insulated resistance values. These values are significantly lower than the experimental Q ambient values due to theoretical insulated resistance values, being an order of magnitude higher than the experimental insulated resistance values.
To calculate the heat transfer rate uncertainty, we will derive expressions for the uncertainty due to the cold output flow rate, T5, and the hot output temperature. Error propagation will be used for unit conversion, such as volumetric flow rate, from length per minute to meters cubed per second. It is assumed that the uncertainty of ambient pressure and specific heat are zero. Shown on the bottom right is a key that states the difference between given values, measured values, derived values, and equations used for these calculations. The accuracy and precision uncertainty for the pressure transducer, flow meter, and thermocouples will also be analyzed. A similar approach is taken for calculating thermal resistance uncertainty. It is assumed specific heat and ambient temperature have an uncertainty of zero. Error propagation is used to account for uncertainty from T-load, cold mass flow rate, T5, and T4 cold. Partial derivatives are determined using an online derivative calculator, and an uncertainty value for R insulated is included to account for experimental values. The goal of week 2 is to experimentally characterize energy transfer at the aluminum block. Seen in figure 4 on the right are equations used for the related load energy balance analysis. Cold air flowing through the load gains energy as heat and causes the temperature of the air to increase. The stations of interest for this stage will be Station 4, related to the cold air at atmospheric pressure, and Station 5, relating to the cool air at atmospheric pressure, seen in figure 5. Using the lumped capacitance method, we can treat the entire load as the same temperature and integrate to determine the total energy change. We will experimentally determine the load material properties and compare them to published values. We will then complete an uncertainty analysis for values relating to the client's goal, including the total transient energy uncertainty. The analysis plan includes observing the effect of pressure on the system by comparing steady state and rise times of the load temperature for each transient response. We will also determine what effect changing the load temperature will have on the rise time and steady state response of the system. Finally, we will validate Q discrepancy and identify how the system can be improved based on sources of error. Thank you for listening to our team's presentation. Please refer to the appendix for any references and equations used to calculate the values seen in this presentation.